My dear students, let me welcome you all to a new edition of physics. And this edition will learn about photoelectricity. Photoelectricity can be defined as production of electrons by electromagnetic radiations. It is the emission of electrons from the surface of some metals when light or electromagnetic waves of certain frequency fall on it. We'll learn about critical frequency, critical wavelength, work function, and we'll learn about how Einstein managed to explain it. So let's get started. Wave particle duality, cathode ray tube. First of all, what about the idea of the cathode ray tube? What about its idea? Yes, it is based on thermionic emission. That's to say, some electrons can escape from the surface of a metal if enough heat is given to the surface. Okay, so the idea, it is based on thermionic emission of electrons, okay, when we raise the temperature of the metal. And what about the structure of the cathode ray tube? Okay, it is shown in front of you. The front part of the tube is the fluorescent screen, and we've got, yes, filament heater. It is the cathode, and function of the cathode is to emit electrons. And we've got something very important because it has great effect on the electrons emitted from the cathode. It is the grid, okay, and we've got an anode. All of these will form something we call electron gun, and to deflect the electronic beam, the electrons emitted from the filament, we use electric fields produced by vertical plates and horizontal plates. So we've got Y plates and X plates. And I'll mention the function of each one of them right now. So talking about the structure of the cathode ray, it consists of, first of all, a heated cathode to produce a beam of electrons. The cathode is a metal surface which is heated by a filament. Then it gives off electrons. Then we've got a grid. And what about the grid? The function of the grid is to control the brightness of the beam. How? It controls the number of electrons that passes through, yes, the grid. Okay? So the grid controls the brightness of the beam. The grid controls the number of electrons per second reaching the fluorescent screen. That is to say, it controls the brightness of the glow. We've got important hints here. The electrical signal in the cathode ray tube, the electrical signal received, controls the potential of the grid. So the grid signal controls the number of electrons per second reaching the fluorescent screen. And that's to say, it controls the intensity of the electronic beam. So it controls the brightness of the luminous spot. We've got an accelerating anode denoted by A1, which accelerates the electrons the ejected electrons to high energy. A1 and A2 form an electronic lenses to focus the electronic beam on the screen. We've got a pair of plates, plates X, to deflect the beam of electrons in the horizontal direction. Vertical plates, yes, deflect the electronic beam horizontally. And horizontal plates, plates Y, deflect the electronic beam in the vertical direction. And what about the function of the fluorescent screen? We've got a screen, fluorescent screen, on which the electronic beam falls. And when electrons falls on the screen, yes, it glows. The screen is coated with zinc sulfide, which emits a blue glow when electrons collide with it. Your attention, please. Increasing the heater current. So when we increase the current that flows in the heater, will increase the number of electrons, okay, emitted from the cathode. And what happens? The number of electrons per second striking the screen will then increase, and so brightness of the luminous spot will be increased. Okay. The brightness will also increase, brightness of the luminous spot, if the voltage of the accelerating anode is increased. The energy of electrons reaching the screen will then increase. And now talking about something very important. Yes, talking about properties of the photons. Okay. Photons, first of all, photons move in space, okay, at the same speed, which is speed of light in space. It is 3 times 10 to the power of 8 meters per second. So all photons in space move with the same speed, regardless of their frequencies, regardless of their wavelengths. Okay, this was the first property. Photons move in space with the same speed. A photon is a discrete amount of energy. It is a packet of energy. Okay, and energy of the photon is determined by its frequency. Once again, a photon is a discrete amount of energy. It is a packet of energy. Energy of a photon is proportional to its frequency, and it is equal to, yes, E is proportional to nu, so E equals Planck's constant nu, h nu. Okay, where h is Planck's constant. And we've got something important, and we've got very important piece of information here. In 1905, Einstein showed that energy has mass according to the equation energy equals mc squared. So energy of the photon equals mc squared, and it is equal to h nu. In this way, we'll be able to determine mass of the photon and momentum of the photon. So photons behaves like particles, and waves, of course, they've got dual property. Okay. So mass of the photon equals h nu over c squared. How? E equals h nu, energy of the photon, in one hand is proportional to the frequency, and from equation of Einstein, it is equal to mc squared, so h nu equals, yes, mc squared. So mass of the photon equals h nu over c squared. And what about the momentum of the photon? momentum is denoted by PL, and it is obtained by the product of mass and speed. Speed of light is given the symbol c, so it is the product of mass and c. Momentum of the photon equals mass times velocity, so it is h nu over c squared, which is the mass times speed is c. One of them will be crossed out, so it is h nu of c. Another property of photons, they exert a force when they are reflected by a surface. This is another property of the photons. They exert a force when they are reflected by a surface. And we'll be able to, yes, obtain an expression that determines this force. If a beam of photons falls on a surface at a rate, yes, of phi, and what about mc? mc is the momentum just before collision with the surface, and photons are elastic. Okay, so they will not lose any of its velocity. It is just, it changes direction when it reflected. So momentum before collision equals mc, momentum after collision equals minus mc. So the change in momentum of one photon due to one collision, we call it impulse of the surface on the photon. Yes, minus mc, it is negative 2 mc. This is the impulse of the surface, effect of the surface on the photon. If we want the effect of the photon on the surface, it will be equal and opposite, so it will be 2 mc. So from Newton's third law of motion, the impulse of the photon on the surface is equal and opposite to that of surface on the photon, so it is equal to 2 mc. So the total impulse of the photons on the surface is equal to, yes, 2 nmc, capital N, yes, denotes the number of the incident photons. 2 nmc, according to Newton's law, second law, it is equal to Ft. So the force equals 2 nmc over T. Nm is the, yes, momentum of the photon, so it is equal to h nu over c. Substituting, so F equals 2 nh nu over Tc. And what about n over T? Yes, it is phi L. It is the rate at which the photons are incident. So phi L equals n over T. So the force equals 2 nh nu over T. And we can say it is equal to, yes, 2 phi L h nu over c. And we've got something very important here. H nu is the energy of the photon. NH nu is the total energy. Total energy over time is power. So the force equals between two brackets, total energy of the incident photons over Ct, and energy over T is power, so the force equals, yes, 2 times the power over C. This is the expression usually used to determine the force of the photons when reflected by a surface. PW is the power of the radiation in watts, of course. We've got important hints here. The force of a beam of photons on a reflecting surface is too weak to affect the surface. When the surface is huge, okay, the force is too weak to affect the surface, but it is appreciably strong if it acts on free electrons, very small particles, then the force of photons on them will be, yes, appreciably strong. And this explains competence effect. Another property, the microscopic view of light, we call it photon model of light, and the macroscopic view of light, light as a wave, goes hand in hand. Okay, how? We'll explain this. In the photon model of light, light is made up of photons. Each photon is a sphere whose radius is roughly equal to the wavelength. That's to say, photons carry the genes of light, which include frequency, speed, and wavelength. But what about the wave? A wave describes the collective behavior of photons. A flux of photons collectively possesses a magnetic field and an electric field. These two fields are mutually perpendicular to each other and perpendicular to the direction of propagation. In fact, the dimensions of the object we are dealing with, the object on which photons fall, determines which view should be adopted. For example, if we are dealing with very minute objects, such as electrons, the microscopic model should be applied. But the macroscopic view should be applied when dealing with the large objects. One more property, a photon has zero rest mass. It loses its mass when it comes to rest. When a photon comes to rest, it loses its mass. The photon is then changed into thermal energy. A photon, as I said, has zero rest mass. And now it's high time to solve a problem. Calculate the force produced by a light beam, 600 nanometer, 100 watt, on a surface when reflecting on it. Let me say it again. Calculate the force produced by a light beam. What about the light beam? Wavelength of the incident light is 600 nanometer, 600 times 10 to the power of negative 9 meter. Its power is 100 watt. Okay, when falling on a surface. Then calculate the mass of a photon of that beam. Speed of light in space is given, 3 times 10 power 8. Planck's constant is given, 6.6 to 5 times 10 to the power of negative 34 joule second. And what effect does this force have on the wall? State how you would expect the effect of the force to differ if the light beam fell on an electron instead of a wall. Okay, we'll take it one by one. First of all, we'll try to determine the force. Force equals 2 times the power over c. Power is given to be equal to 100 over speed of light in space, 3 times 10 to the power of 8. The force is 6.667 times 10 power negative 7 Newton. And what about the mass of the photon? It is h nu over c squared. Okay, it is 6.625 times 10 to the power of negative 34. Why? Simply because nu is, yes, replaced by c over lambda, and one of the two c's is crossed out, so it is 6.625 times 10 to the power of negative 34, over 3 times 10 to the power of 8, wavelength 600 nanometer, it is converted into meter, it is multiplied by 10 to the power of negative 9. The mass is 3.68 times 10 to the power of negative 36 kilogram. Of course, the force is too small, it is too diminutive to affect the surface, but it has a considerable effect on the electron. And now talking about wave properties of a particle. Louis de Broglie hypothesis. What about this hypothesis? Any moving particle associates with it wave-like properties. Any moving particle associates with it, yes, wave-like properties. The wavelength of that wave is determined by the relation, yes, wavelength lambda equals h over mv. mv is the momentum of the moving particle. So lambda equals h over pl, where pl is the linear momentum of the moving particle. Momentum, which is the product of mass and velocity. H, of course, is Planck's constant. Example for the wave properties of a particle. The stream of electrons associates with it a wave. The wavelength of this wave is determined from, yes, the expression lambda equals h over mv. Lambda equals h over pl, where m is the mass of the electron and v is its velocity. This wave can show diffraction, refraction, reflection, and interference. Your attention, please. The dual nature of a photon can be proved as follows. To prove that lambda is inversely proportional to the momentum, mass of the photon is determined from the expression h nu over c squared. Nu equals c over lambda. So the mass is determined from hc over lambda c squared. One of them will be crossed out. So lambda equals h over mc. mc is the momentum. So lambda equals h over pl. So lambda is inversely proportional to the momentum. Another method, since c equals lambda nu, so lambda equals c over nu. Multiplying by Planck's constant, denominator and numerator. So lambda equals h nu over, so lambda equals hc over h nu. It can be rearranged. It is equal to h over h nu over c. And what about h nu over c? It is the momentum of the photon. So lambda equals h over pl. So lambda is inversely proportional to the momentum. And now talking about the electron microscope. It is the structure and the function mode of work of the electron microscope is shown in front of you. Okay? We've got a cathode. Function of the cathode is to emit. Function of the cathode is to emit beam of electrons. And then we've got an anode. The potential difference between the anode and the cathode is so high, that is to accelerate the electrons to very high velocity. In this way, wavelength is decreased and magnification, high magnification is obtained. Okay, and we've got F1, it is condensing lens. What about the condenser. Usually it is a magnetic lens whose function is to converge the beam of electrons upon the examined object. And we've got, yes, objective lens, f2, and also it is a magnetic lens whose function is to give an intermediate image, and f3, yes, magnetic lens also whose function is to produce a final image on a fluorescent screen or photographic plate. So electron microscope depends in its operation on the wave nature of electrons. It resembles the optical microscope in many ways. The electron microscope has very high resolving power. The question is why? Because by accelerating the electrons, the wavelength of the accompanying wave, wavelength lambda, since it is equal to h over mv, m is the mass of the electron and it is constant. By increasing the velocity, increasing v, lambda decreases, and in this way high magnification is obtained. In this way we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.